Tonight, we're going to explore a question almost everyone has asked at some point, usually late at night, usually without ever getting a satisfying answer. What's at the edge of the universe? It feels like it should have a simple answer. Everything else in your experience has an edge. Rooms have walls. Oceans have shores. Even the largest things you can picture. Continents, planets, solar systems. Eventually run out, give way to something else, mark a boundary you could, in principle, stand at and look beyond. Tonight, we're going to discover that this question, asked about the universe itself, quietly contains three completely different questions, tangled together, and that once you carefully pull them apart, something remarkable happens. The question doesn't just go unanswered, it dissolves entirely, replaced by something stranger, and in its own way, considerably more comforting. Here's where we'll end up, stated plainly, right at the start, so you can settle into the journey rather than wait anxiously for the destination. There is no edge. Not because it's too far away to reach. Not because our telescopes aren't yet powerful enough. Because the very geometry of space, as best as an entire century of physics has ever been able to determine, simply doesn't contain one. Anywhere, in any direction, under any of the possibilities modern cosmology takes seriously. For most of human history, and honestly, for most of scientific history too, the universe was pictured as a container. A great sphere, or a great room, holding stars and planets the way a jar holds marbles. It's a completely natural way to think, built directly from a lifetime of experience with things that have insides and outsides. Then, in 1915, a German physicist reworked our entire understanding of what space actually is. Albert Einstein's general theory of relativity didn't simply add a few new rules to the existing picture of the cosmos. It replaced the picture entirely. Before 1915, physicists, following Isaac Newton, largely imagined space as a fixed, unchanging stage. A rigid, three-dimensional grid, sitting quietly in the background, upon which everything else in the universe played out its own story. Einstein showed that space itself is not fixed at all. It bends, it stretches, it curves in response to the matter and energy moving through it. Space, in the modern picture, is not a stage. It's closer to a genuine participant in its own right. Dynamic, flexible, capable of expanding, contracting, and curving all on its own. The first surprise is that space itself is not a container at all. It's a dynamic, flexible geometry with no requirement that it sit inside anything larger. The second is that the universe stubbornly, comprehensively refuses to have a center. And it turns out to be remarkably difficult to have an edge without one. And the third, the part this entire documentary is really about, is that every single mathematically permitted shape the universe could actually have, every one, turns out to be edgeless for reasons that have nothing to do with distance and everything to do with geometry itself. By the end of tonight, you're going to understand exactly why cosmologists are confident there is no edge to find, what the boundary we actually do experience really is, and why that boundary, rather than being a disappointment, might be one of the most quietly comforting facts in all of astronomy. Let yourself settle in. There's nothing you need to solve tonight, only to let an old, familiar question slowly come apart, gently, into something calmer than it started as. Here is where tonight's journey will take us. We'll begin by separating three entirely different ideas that all hide inside the single, simple-sounding phrase, the edge of the universe. Because most of the confusion in this question comes from mixing them up without realizing it. We'll discover why the universe refuses to have a center, and why that refusal turns out to be the first serious blow against the very idea of an edge. We'll walk through the small menu of shapes space is actually allowed to take according to general relativity, and discover that every single one of them, without exception, has no boundary at all. We'll look at what our most precise instruments have actually measured about which of those shapes we live inside, and sit honestly with the parts of that measurement still being argued over today. We'll spend real time with the strange, genuinely mind-bending idea that something can be completely finite in size and still have absolutely nowhere you could ever call an edge. We'll meet the boundary that does exist. Not a wall in space, but a horizon, built entirely from the simple fact that light takes time to travel, and discover that every single observer in the universe, on every world, around every star, carries their own version of it. And we'll end, as we always do, by turning this back toward what it actually means to exist at the exact center of everything you will ever be able to see. Not because you're special, but because everyone, everywhere, always is. Before we dive in, if questions about the true shape of the cosmos are the kind of thing that helps quiet your mind at the end of a long day, consider liking this video or subscribing to the channel. It's a small thing. It costs you nothing. But it helps this kind of slow, patient science storytelling reach the people who need exactly this, tonight. Now, let's begin. When someone asks what's at the edge of the universe, they are almost always asking one of three genuinely different questions, without realizing it. And untangling those three questions turns out to be the single most important thing we can do tonight, before anything else makes sense. The first question, which we'll call meaning A, is really asking about the edge of what we can see. This is what astronomers call the observable universe. A vast, spherical region, centered on Earth, containing everything whose light has had time to reach us in the roughly 13.8 billion years since the Big Bang. Its radius today, accounting for the ongoing expansion of space during that light's long journey, comes out to approximately 46.5 billion light years. This particular edge is real, well measured, and, once you understand it properly, almost mundane. It is a limit on our information, not a wall anywhere in space. Think of it exactly like the horizon at sea. A ship sitting at your own horizon doesn't experience anything unusual from its own deck. Its horizon simply lies about 5 kilometers away in every direction, exactly the way yours does, wherever you happen to be standing. The second question, meaning B, is asking something considerably deeper, whether space itself might simply stop somewhere. A place where, if you flew far enough in a straight line, there would be no more forward left to fly into. This is a genuine, serious question about geometry and topology, not a question about the limits of our telescopes. General relativity does technically permit spacetimes with boundaries, in principle, but the standard, best supported models of our actual universe contain none. And, crucially, not a single observation, in over a century of increasingly precise cosmology, has ever hinted that one exists. The third question, meaning C, is really asking about the wall of a container. The intuition, built from an entire lifetime of ordinary experience, that the universe must be an object sitting inside some larger space, the way a fish tank sits inside a room. This intuition, however natural it feels, smuggles in a hidden assumption that modern physics simply doesn't support. In the standard cosmological picture, space-time itself is the entire arena. There is no outside for an edge to face into. Asking what lies beyond the edge of the universe, in this specific sense, turns out to be a bit like asking what lies north of the North Pole. A question that sounds perfectly grammatical, right up until you realize the concept of north simply stops applying at that exact point, not because you've run out of room to search, but because the question itself has quietly stopped making sense. It's worth sitting with the North Pole example a little longer, because it's genuinely instructive, rather than just a clever turn of phrase. Standing anywhere else on Earth, north is a perfectly meaningful direction. You could point toward it, walk toward it, get measurably closer to it. But standing exactly at the North Pole itself, every single direction you could possibly face is south. North has not become difficult to find. It has become a category error, a direction that simply no longer applies, given where you happen to be standing. Physicist Stephen Hawking used exactly this comparison in his own writing, precisely because it captures something true about certain questions that sound coherent in ordinary language, while quietly assuming a structure the actual situation doesn't possess. What's beyond the edge of the universe may belong to that same family of questions, grammatically perfect and structurally empty. Here's an analogy worth holding on to for the rest of tonight's journey, because we'll return to it more than once. Imagine a fish swimming in the middle of the open ocean, 1,000 kilometers from any coastline in any direction. That fish could swim its entire life. At a modest 5 kilometers an hour, covering perhaps 10,000 kilometers across a full lifetime of wandering, and never once encounter anything but more water. Its failure to find an edge tells it something real and true about the ocean it lives in. But a shark, on the exact opposite side of the planet, is having the identical experience at the identical moment. Neither of them is anywhere near an edge. The concept simply doesn't apply to their world the way it would apply to a fish living in a small glass tank. There's a second image worth carrying alongside the fish, because it captures the distinction between meaning A and meaning B especially well. The difference between the two is the difference between fog and a fence. Fog limits how far you can see, and it moves with you, wherever you go, always keeping you at its own center. A fence is a real, physical structure, sitting at a fixed place in the world, entirely indifferent to where you happen to be standing. Nearly everything in tonight's story comes down to a single discovery, patiently assembled across a century of cosmology. The universe, as far as anyone has ever been able to measure, is full of fog, and appears to contain no fences at all. The first serious blow against the idea of a cosmic edge comes from a direction most people don't expect. It isn't a direct search for a boundary at all. It's a simple, stubborn, repeatedly confirmed observation. The universe refuses to have a center. And it turns out to be remarkably difficult to have an edge without one. Cosmologists describe this refusal using something called the cosmological principle. The idea that, on sufficiently large scales, roughly 100 to 300 million light years and beyond, the universe looks statistically the same in every direction and from every location. It sounds like a modest claim. The evidence behind it is anything but modest. Consider the faint, ancient afterglow of the Big Bang itself. Radiation called the cosmic microwave background, filling the entire sky, in every direction, left over from a time when the universe was only about 380,000 years old. When astronomers measure its temperature across the entire sky, they find it astonishingly uniform, varying by only about 1 part in 100,000 from one patch of sky to any other. If the universe had a genuine edge somewhere, you would expect regions closer to that edge to look noticeably different from regions far from it. Fewer galaxies scattered on one side, a gradual gradient building across the sky as you approach the boundary. No such gradient has ever been found, anywhere, in any direction anyone has ever pointed a telescope. Large-scale galaxy surveys tell the exact same story. Projects cataloguing millions of individual galaxies, mapping out the vast cosmic web of filaments and empty voids stretching across billions of light years, find the same overall statistical texture, repeating no matter which direction you look or how far out you measure. This matters more than it might first appear to, because an edge implies a middle. Every bordered object you've ever encountered, a coin, a continent, a crowd gathered in a room, has some kind of geometric center, sitting at a specific distance from every edge. And the entire history of astronomy, going back to Copernicus, has been one long, repeated demotion of our own presumed importance. Earth turned out not to be the center of the solar system. The sun turned out not to be the center of the galaxy. The cosmological principle represents the final, most radical step in that same long demotion. There is no special position anywhere in the universe at all. Any observer, on any galaxy, anywhere, measures the exact same large-scale averages we do from wherever they happen to be standing. A short pause here, if you'd like one. It's a genuinely large idea to sit with. An entire universe, with no one place more central than any other. Let it settle slowly, the way starlight itself does. We'll continue when you're ready. There's a classic analogy worth walking through carefully here, because it's genuinely illuminating, provided you follow it all the way to its own limits. Imagine a loaf of raisin bread rising slowly in an oven. As the dough itself expands, every single raisin moves steadily away from every other raisin, all at once. From the point of view of any one particular raisin, every other raisin appears to be receding, and the most distant ones appear to recede fastest of all. Remarkably, every raisin, wherever it happens to sit inside the loaf, sees itself as the apparent center of this expansion, and every single one of them is, in its own local sense, equally correct. Here's the crucial subtlety, the part where the analogy needs to be pushed further to actually work. A real loaf of bread, sitting in a real oven, does have an actual edge and an actual center, a crust and a middle. To make the analogy match the real universe, you have to imagine the dough extending forever in every direction, with no crust at all, or curving back around on itself in some higher dimensional way we'll explore in the next chapter. Remove the crust from the analogy, and you remove the center along with it, leaving nothing behind but an endless, evenly expanding texture, with no privileged raisin and no privileged position anywhere at all. Einstein's equations, the mathematical foundation of general relativity, don't simply declare what shape the universe must be. They offer something closer to a short, carefully limited menu. And once you demand that the universe looks statistically the same everywhere, the way Chapter 2 just established it genuinely does, that menu narrows down to exactly 3 possible options. The first option is a closed universe, sometimes described as spherical or positively curved. Picture the 3-dimensional equivalent of the surface of a sphere. Mathematicians call it a 3-sphere, where space itself curves back around on its own. In this geometry, the total volume of the universe is finite. Travel far enough in a perfectly straight line, and you would, eventually, return to precisely where you started. Parallel lines drawn in this geometry gradually converge toward each other, and the 3 angles of an enormous triangle drawn across this space would add up to slightly more than 180 degrees, a small but measurable departure from the geometry taught in an ordinary classroom. This particular shape carries a genuinely strange property, one we'll spend real time with in a few chapters. It is completely finite, and yet, remarkably, contains no edge whatsoever. The second option is a flat universe, the ordinary, familiar geometry of a tabletop, extended forever in every direction, without limit. In this geometry, parallel lines remain perfectly parallel, no matter how far you extend them. Triangle angles add up to exactly 180 degrees, precisely as expected. And the total volume, in the simplest version of this geometry, is genuinely infinite. There is no edge anywhere to walk toward, because an infinite plane, by its very definition, has no boundary at all. The third option is an open universe, sometimes called hyperbolic, the 3-dimensional equivalent of a saddle shape, or the surface of a Pringles potato crisp, curving continuously away from itself in every direction. Here, parallel lines gradually diverge from one another, spreading further and further apart the longer you follow them. Triangle angles add up to less than 180 degrees. And like the flat case, this geometry extends infinitely in every direction, with no edge anywhere to be found. Here is the single most important sentence in this entire chapter, worth sitting with directly. None of these 3 options, taken from the complete list of possibilities general relativity actually allows, contains an edge anywhere. This isn't something astronomers had to go out and measure. It falls directly out of the underlying mathematics, the moment you require that the universe look the same in every direction. A requirement Chapter 2 already showed us, repeatedly, decisively, holds true. A genuine boundary would require the cosmological principle to fail at some specific location. some place where the universe suddenly, inexplicably stopped looking like itself. No such failure has ever been observed, which means the real empirical question left for the next chapter isn't whether an edge exists at all. It's simply and only which of these three perfectly edgeless geometries we actually happen to live inside. There are some genuinely useful, sensory ways to feel the difference between these three shapes, rather than simply hearing them described mathematically. For the closed geometry, picture walking the surface of the Earth itself. Head off in any consistent direction with a good compass, and given enough time, you would eventually circle the entire globe and arrive back where you started. At an ordinary human walking pace, circling Earth's roughly 40,000 kilometer circumference would take somewhere around 8,000 hours of continuous walking, the better part of a full year. A closed universe works by the exact same underlying logic, just extended into 3 full dimensions rather than 2. Though any actual circumnavigation would unfold on a scale vastly larger than anything currently within our observable horizon. For the flat geometry, picture an enormous sheet of paper extending outward past every horizon you could possibly imagine, forever, with no edge in any direction. And for the open geometry, picture an endless, saddle-shaped landscape where every direction you walk, the land curves gently away beneath your feet. Something like descending from a mountain pass that simply never, ever ends, with more room surrounding you at every step than ordinary flat geometry would ever allow. So, of the 3 edgeless geometries available, which one do we actually live inside? This is where cosmology stops being pure mathematics and becomes something you can genuinely go out and measure, using one of the most elegant tricks in all of observational science. The method is a form of triangulation conducted on the largest possible scale anyone has ever attempted. The cosmic microwave background, that ancient afterglow of the Big Bang we met in the last chapter, carries within it a natural, physical ruler, something called the sound horizon. The precise distance pressure waves could travel through the hot, dense plasma filling the infant universe during its first 380,000 years of existence. Physicists can calculate the true length of this ruler directly from well-understood early universe physics. And when they look at the sky, they can measure its apparent angular size as well, coming out to almost exactly 1 degree. Here's where the geometry test actually happens. If space is flat, light from the cosmic microwave background would have traveled to us along perfectly straight, Euclidean paths, and the ruler's apparent angular size would match a specific, precisely calculable prediction. If the universe were closed instead, the converging geometry would make that same ruler appear artificially magnified, larger than the flat prediction. If the universe were open, the diverging geometry would make it appear artificially shrunken, smaller than expected. It's the exact same underlying logic as drawing a triangle on the surface of a balloon, compared to drawing that same triangle on a flat sheet of paper. Except here, the triangle's own baseline spans the entire width of the observable universe. The headline result, gathered by the European Space Agency's Planck satellite, combining measurements of the cosmic microwave background with a separate technique called baryon acoustic oscillations, drawn from large-scale galaxy surveys, finds that the universe is flat to within about 0.2%. The specific curvature value that comes out of this combined measurement is small enough, and close enough to exactly 0, that if there is any genuine curvature to space at all, its radius must be vastly, almost incomprehensibly larger than our entire observable universe. A short pause here, if you'd like one. Take a moment to simply picture it. An entire satellite, orbiting patiently, reading the oldest light in existence, just to answer a single question about the shape of everything. We'll continue shortly. It's worth pausing here and being fully honest with you about a genuine complication in this measurement, exactly the way a careful scientist would be honest with you, rather than smoothing over the details for the sake of a tidier story. In 2019, a team of researchers pointed out something genuinely puzzling. When you look at Planck's measurement of the cosmic microwave background's temperature pattern entirely on its own, without combining it with the separate galaxy survey data, it shows a modest but statistically real preference for a slightly closed universe instead of a perfectly flat one. Strong enough that the researchers, only half-jokingly, titled their paper, "A Possible Crisis for Cosmology." However, that particular preference weakens considerably and actively conflicts with the data the moment you properly include additional measurements of gravitational lensing and the galaxy survey information. Most cosmologists, examining the full combined picture, still read the evidence as genuinely, comfortably flat. But the underlying anomaly in the Planck-only data is real, and it remains actively studied rather than fully, cleanly resolved. Here's a way to actually feel just how precise flat to 0.2% really is. If the universe genuinely does curve, even slightly, imagine it as an enormous sphere. So enormous that our entire 46.5 billion light-year observable patch would sit on its surface like a single postage stamp, placed on a balloon far, far larger than anything we could ever hope to see in full. Walking across a stamp that size, at an ordinary human walking pace, would take somewhere in the neighborhood of 10 to the 23rd power years. Roughly 1 trillion times longer than the entire current age of the universe itself. From inside a stamp that's small relative to the whole, the difference between perfectly flat and very slightly curved becomes almost impossible to distinguish without genuinely extraordinary precision. Planck is exactly that kind of extraordinarily precise instrument. And for now, overwhelmingly, it says flat. This next chapter exists to gently take apart the single most stubborn intuition standing between most people and a genuine, felt understanding of tonight's answer. The deeply ingrained assumption that finite and bounded must always travel together, as though anything with a limited size must, somewhere, have an edge marking where that size runs out. Let's build this up slowly, using an analogy that has been guiding people through exactly this confusion since not long after Einstein himself first published his own theory of general relativity in 1915. Imagine an ant living its entire life on the surface of a balloon. The ant's entire experience of the world is two-dimensional. It can move forward and back, left and right, but it has absolutely no access to and no concept of up off the curved surface it lives on. The balloon's surface itself is genuinely finite in area. If the balloon happened to be Earth-sized, its surface would cover roughly 510 million square kilometers, a large but entirely definite, entirely finite number. Einstein himself used a version of this exact image in his own popular writing on relativity, specifically because he recognized how difficult this particular idea is for the human mind to hold on to without some kind of physical picture to anchor it. We are, every one of us, creatures who evolved navigating a world with edges, riverbanks, cliff faces, horizons that genuinely did mark the limit of what our ancestors could safely explore in a single day. Asking that same evolved intuition to comfortably hold finite yet edgeless is asking it to do something it was never built for. The balloon, and the ant walking patiently across its surface, exists specifically to give that intuition somewhere solid to stand, even while the deeper idea it's illustrating remains genuinely counterintuitive. And yet, that ant could walk in any direction it chose for its entire lifetime and never once encounter an edge, never find a seam, never arrive at a place where the ground beneath its feet simply stopped, giving way to some kind of void beyond it. If it walked in a single, perfectly straight line for long enough, on an Earth-sized balloon, that would mean covering the planet's roughly 40,000 kilometer circumference. It would eventually return to precisely where it started, arriving, strangely, from the exact opposite direction it originally set out in. At a typical ant's walking speed, that full circumnavigation would take somewhere around 42 years of continuous, unbroken walking. An entire ant lifetime repeated several times over. But the destination, however distant, would always be the same familiar starting point, approached now from behind, rather than any kind of genuine boundary. Now, Lift this exact same idea up by one additional dimension, and you have precisely the situation a closed universe would present. The ant's two-dimensional surface becomes our own three-dimensional space. Every direction you could possibly point a spacecraft lies directly on that same curved surface. There is no direction in space that points meaningfully outward, away from the universe as a whole. For the exact same reason that up, away from the balloon, simply isn't a direction available to an ant confined entirely to its curved, two-dimensional surface. Here's why this genuinely matters for tonight's central question. If our universe does turn out to be the closed geometry, and Chapter 4's measurement showed us we're extremely close to flat, though a very slight closure remains within the current margin of measurement error, then several things would all be true simultaneously. The universe's total volume would be finite. The total number of galaxies it contains would be finite. And still, no traveler, however patient, however advanced, however much time they were willing to spend, could ever reach an edge. Because, quite simply, there isn't one to reach. Finiteness, in this specific geometric sense, works something like the finiteness of Earth's own oceans, genuinely bounded in total amount, and yet, for all practical purposes, entirely unbounded in how far you could wander through them without ever finding a shore. There's a gentler, more familiar example of exactly this same idea, hiding in plain sight in a place most of us have never thought to look for it, time itself rather than space. A circle is finite. You could measure its exact total length, and yet it has no endpoint anywhere along its circumference. A calendar year is finite too, 365 days, a definite, countable quantity. And yet December doesn't border some kind of empty void once it ends. It simply loops, seamlessly, back around into January. A closed universe, in this specific and genuinely useful sense, is nothing more exotic than space itself adopting the same basic topology as a loop, finite in extent, and utterly, structurally incapable of ever presenting you with an edge, if it turns out the universe is flat or open rather than closed. And current measurements genuinely can't yet rule either possibility out. The answer to tonight's central question becomes, in its own way, even simpler and even stranger. In either of these two geometries, space extends infinitely in every direction, meaning there is, quite literally, more universe waiting in every possible direction, forever, without any limit at all. Here's the everyday mistake worth clearing up directly, because nearly everyone makes some version of it. We tend to treat the word infinite as though it simply meant very, very far away. An extreme version of distance, sitting somewhere at the far end of an extremely long journey. But infinity isn't a destination waiting at the end of a sufficiently long trip. It's the complete absence of any end to that trip in the first place. A traveler moving through an infinite, flat universe would face the exact same situation after traveling 1 kilometer as they would after traveling 10 to the 25th power kilometers. More universe ahead of them in absolutely every direction, always, without exception. No finite speed changes this fact in any way. Not walking at an ordinary human pace, and not even light itself. Traveling at its own maximum possible speed of 299,792 kilometers every single second. After any finite amount of travel time whatsoever, no matter how long, the remaining distance to the edge would still, necessarily, be infinite. Here's an image that might help this land more intuitively. Imagine an enormous library whose rooms simply repeat and vary without any end at all. You could walk through a full 1,000,000 rooms every single day for an entire human lifetime, and by the very end of that lifetime, you'd have seen somewhere around 30 billion individual rooms. A genuinely enormous number by any ordinary measure. And the library, at the end of all that walking, would not be one single room closer to actually ending. There is no final room waiting somewhere ahead, and so there is no wall marking the end of the entire collection. An infinite universe works by that exact same logic. The persistent failure to ever find an edge isn't some limitation of how far or how fast you've managed to travel. It's simply, structurally, a fundamental property of the building itself. A short pause here, if you'd like one. There's no need to picture all 30 billion rooms. Just the simple, quiet fact of a library that never runs out. Let that image rest, and we'll continue. There's a genuinely strange, almost dizzying implication worth mentioning here, though it's important to be honest about exactly how speculative it actually is. In a universe that's genuinely infinite, containing only a finite set of possible ways matter can actually be arranged in any given, bounded region of space, a curious mathematical consequence follows. Everything that can possibly happen does happen, infinitely many times over, somewhere out in that endless expanse, including, by one well-known theoretical estimate, exact duplicates of you reading these very words, somewhere within a distance so large it can only be written using an exponent stacked on top of another exponent. It's a genuinely fascinating thought experiment, worth sitting with for its sheer strangeness. But it's crucial to be clear about what it actually is. A plausible mathematical extrapolation from an infinite universe, not something anyone has ever observed, or could ever hope to observe directly. It belongs, honestly, in the same category as several other ideas we'll revisit later tonight. Genuinely interesting, entirely unconfirmed. Here's the punchline this chapter has been building toward, and it's worth stating plainly, because it ties directly back into everything covered so far tonight. Whether the universe turns out to be closed and finite, the subject of the last chapter, or flat and open and infinite, the subject of this one, the actual experience of any traveller, anywhere, turns out to be exactly, precisely identical. There is no direction you could travel, for any conceivable length of time, at the end of which you would arrive at the edge of space itself. Infinity is edgeless simply by exhaustion. There's always more, no matter how long you search. Finitude, in the closed case, is edgeless by curvature. You'd eventually just return to where you started. Either way, however the true shape of the universe eventually turns out, the answer to tonight's title question remains exactly, comfortingly the same. No edge. We've now spent 6 full chapters carefully establishing that there is no edge to space itself, under any geometry current physics takes seriously. But there is a boundary in this story. A real, measurable, honestly fascinating one. It simply isn't the kind of boundary the question originally assumed. Let's meet it properly now, and understand exactly why it's so easy to mistake for the thing we've spent all night ruling out. Light is extraordinarily fast, but it is not infinitely fast. It travels at a fixed, finite speed. 299,792 kilometers every second. And the universe, while genuinely enormous, is not infinitely old. It has existed for a finite span of time, roughly 13.787 billion years. Put those two finite numbers together, and something inevitable follows. There is a maximum possible distance light could have travelled to reach us in all the time since the universe began. Astronomers call this the particle horizon. And thanks to the ongoing expansion of space itself, stretching out the path that light has travelled along its entire journey, that horizon sits, today, at a commoving distance of approximately 46.5 billion light-years. Anything beyond that distance isn't missing, and it certainly isn't non-existent. Its light, quite simply, hasn't had time to reach us yet. It's still on its way. Here's the detail that trips up almost everyone encountering this fact for the first time, and it's genuinely worth sitting with slowly, because the numbers seem, at first glance, to directly contradict each other. The universe is roughly 13.8 billion years old, and yet our observable horizon sits at 46.5 billion light-years away. More than 3 times farther than light could seemingly have travelled in that amount of time. How is that possible without breaking the universe's own speed limit? The resolution lies entirely in the expansion of space itself. Consider a galaxy whose light took, say, 13.4 billion years to finally reach us. During that entire multi-billion-year journey, the space between that galaxy and Earth has itself been continuously stretching, expanding, carrying the galaxy's present-day position considerably farther away than it originally sat when the light first departed, out to somewhere over 33 billion light-years away by the time that ancient light finally arrives here tonight. This isn't a violation of relativity's speed limit at all, because that speed limit governs motion through space, not the stretching of space itself. Both numbers, the 93 billion light-year diameter of our observable universe and the 13.8 billion year age of the universe as a whole, are completely, simultaneously correct. They're simply answers to two entirely different questions. There's a second, quieter, considerably sadder horizon worth knowing about too, one that exists precisely because the universe's expansion isn't merely continuing. It's accelerating, driven by the still mysterious force cosmologists call dark energy. This second boundary, called the cosmic event horizon, sits at a commoving distance of roughly 16 billion light-years. Anything happening beyond that distance, right now, tonight, can never signal us, ever again, no matter how long we wait, because the space between us and that event is stretching faster than light itself could ever hope to close the gap. Galaxies we can still see tonight, their ancient light still arriving after its long journey, are, in a very real sense, already crossing over into this permanent silence, drifting steadily beyond the point where any future signal from them could ever reach us. Current models suggest that roughly 100 billion years from now, observers looking outward from whatever remains of our own galactic neighborhood may see a universe that appears to contain essentially no other galaxies at all. Not because those galaxies stopped existing, but because every single one of them will have permanently crossed beyond this quiet, expanding horizon. There's something worth sitting with in the strange asymmetry between these two horizons, the particle horizon and the event horizon, because they tell almost opposite stories about time. The particle horizon, at 46.5 billion light-years, is a boundary that grows outward, patiently, delivering us more of the universe's past with every year that passes. A gift arriving continuously, forever. The event horizon, at 16 billion light-years, is a boundary that quietly closes, taking away our access to the universe's future, one galaxy at a time, forever. We are, in this specific sense, simultaneously gaining access to more of the ancient past and losing access to more of the unfolding future, both at once, every single night, without ever noticing either process directly happening. Here, finally, is the fog analogy completed after being introduced all the way back at the start of tonight's journey. The observable universe genuinely is fog in the most precise sense available. It's a soft, spherical boundary centered entirely on you, defined by nothing more mysterious than your own particular history and vantage point. A boundary that recedes further outward the longer you patiently wait, and that moves seamlessly along with you, wherever you happen to be standing. Nobody in the entire history of astronomy, not us, not any civilization anywhere else in the universe, has ever actually observed a fence. This is the chapter where two separate threads from earlier tonight, the complete absence of any center and the real, personal nature of the observable horizon, finally weave together into the single central image this entire documentary has been quietly building toward. Because every observable horizon is defined entirely by an individual observer's own unique position in space and time, every single point throughout the entire universe carries its own private, personal, observable universe. In exactly the same way, every individual walker, moving through a thick, enveloping fog, carries their own private circle of visibility along with them, wherever they go. We sit at the exact center of our own observable universe, not because the cosmos somehow arranged itself specifically around the Milky Way out of some special favor. We sit there because being at the center of your own personal light cone is the one single position that every observer, everywhere, without exception, necessarily occupies, no matter where they happen to be standing. A philosopher named Nicholas of Cusa anticipated this exact insight, remarkably, all the way back in 1440, describing the universe as a sphere whose center is genuinely everywhere and whose circumference is nowhere at all. Let's make this vivid with a concrete example. Imagine a civilization on some world orbiting some star, sitting a full 30 billion light years away from us in comoving distance. At this exact same moment in cosmic history, their own astronomers would measure the very same cosmic microwave background temperature we do. They would calculate the very same 13.8 billion year age for their universe. And they would find their own observable horizon sitting at the very same 46.5 billion light years away, centered entirely, precisely on them. We would sit comfortably inside their own observable universe, occupying no special position whatsoever from their own particular point of view. Their night sky, examined carefully in every direction, would show the exact same underlying statistical uniformity ours does, and their own cosmologists, running the exact same kind of careful analysis described across tonight's entire documentary, would arrive at the exact same conclusion we have: no center and no edge anywhere. The cosmological principle guarantees that the entire argument of tonight's story could be written, essentially word for word, from any planet, orbiting any star, in any galaxy, anywhere across the whole of existence. A brief pause here, if you'd like one. Picture that distant world for a moment. Its own sky, its own patient astronomers, working out the exact same gentle truth we've spent tonight assembling. We'll continue when you're ready. Here's one more sensory way to feel this, building directly on our earlier image of a lone ship encountering another out at sea. At sea, your own personal horizon typically sits about 5 kilometers away, given an ordinary eye height of a couple of meters above the waterline. When another ship appears, rising slowly over that horizon, it isn't arriving from some special place called the edge of the ocean. It's simply arriving from the middle of its own particular patch of water, sailing along entirely unaware that, from your specific vantage point, it briefly appeared to emerge from nothing at all. Every single sailor who has ever put out to sea owns their own personal horizon. Not one of them has ever, in the entire history of seafaring, owned the ocean's actual edge. Because the ocean, vast as it is, genuinely has one, somewhere, eventually. The universe, as best as we can currently tell, does not. To really feel how enormous our own personal horizon actually is, compared to anything human beings have ever physically reached, consider Voyager 1, humanity's farthest traveling spacecraft, coasting steadily outward at roughly 17 kilometers every second since its launch in 1977. In nearly half a century of continuous, uninterrupted flight, it has covered a total distance of roughly 25 billion kilometers, which works out to approximately 0.0026 light years. That represents somewhere around 1/18 millionth of the entire distance separating us from our own observable horizon. At that same steady pace, simply reaching the very edge of our own personal fog bank. Not the edge of the universe itself, just the current limit of what any human being has ever been able to observe, would take something in the neighborhood of 10 to the 17th power years, 10 million times longer than the entire current age of the universe. And if the whole of the universe genuinely does turn out to be infinite, as roughly half of tonight's story has suggested it very well might be, then whatever lies beyond even that unimaginably distant horizon isn't merely far away. It simply doesn't exist, in the specific sense of being something anyone could ever, even in principle, eventually reach. Before we move into tonight's closing chapters, I want to slow down and be honest with you about something, because in a sleep documentary especially, admitting exactly what remains genuinely unknown can be one of the most calming moves available, rather than the most frustrating one. Science resting comfortably inside its own honest uncertainty is a genuinely peaceful thing to witness once you stop expecting every question to have a tidy, finished answer. The first open question involves something called topology, a subtly different concept from the curvature we spent real time with a few chapters ago. Curvature describes the local shape of space, and as we've discussed, it has been measured with real precision. Topology describes something else entirely, the overall global connectivity of space, and it remains, honestly, barely touched by current observation. A universe could, in principle, be perfectly flat in its local curvature and still be finite overall, curled up on itself the way an old video game screen lets your character fly off the right edge of the map, only to reappear instantly from the left. Astronomers have actually searched for direct evidence of this kind of wraparound, looking for matching, repeated patterns in the cosmic microwave background, patterns that would appear if we were somehow seeing the same distant region of space twice from two different directions. These searches have found no such matches, ruling out any wraparound smaller than our own observable horizon. But a universe that wraps around on a scale only slightly larger than that horizon would be, honestly, completely indistinguishable from a universe that simply goes on forever. A genuinely open question, possibly permanently so. The second open question is that Planck-only curvature anomaly we discussed back in Chapter 4. The mild, statistically real preference for a slightly closed universe, visible only when you examine the cosmic microwave background data entirely on its own, without the additional galaxy survey information. It remains genuinely unresolved whether this anomaly points towards some subtle, undiscovered new physics, a hidden systematic error somewhere in the data, or simply an unlucky statistical fluctuation. Several major observational projects, currently underway or coming online through the rest of this decade, are specifically designed to sharpen this exact measurement considerably. For now, it remains an honest, openly acknowledged loose thread. The third open question is, in some ways, the most philosophically striking of the entire documentary. There is a genuine, almost theorem-like limit on what any observer, anywhere, could ever hope to determine about the true, total shape of the universe. From inside any single, finite, causally connected patch of space, which is, necessarily, all any observer could ever occupy. No conceivable experiment could ever fully distinguish the universe is genuinely infinite from the universe is finite, but simply larger than we will ever be able to see. This isn't a temporary technological limitation, waiting patiently for some future, more powerful instrument to finally resolve it. It may be a permanent, principled boundary on what observation itself can ever tell us. Not because we lack sufficient cleverness, but because the necessary information, quite literally, cannot physically reach us, no matter how long we wait or how carefully we look. And a fourth question, worth mentioning honestly while being equally clear about how speculative it currently is. Some cosmological models, built around a theory called eternal inflation, generically predict the existence of a much larger multiverse containing countless separate bubble universes existing entirely beyond our own observable horizon. These remain genuinely speculative extrapolations of otherwise well-supported inflationary physics. Fascinating, worth knowing about, and, for now, entirely beyond any observational test we currently have any way of conducting. Here is the single honest sentence I'd offer to summarize this entire chapter, and really, this entire documentary. We can say, with real data-backed confidence, that the universe shows no observed edge anywhere, and that it measures flat to within roughly 0.2%. We can say, with genuine mathematical certainty, that every geometry general relativity permits is completely edgeless, without exception. And we have to admit, honestly, openly, that the true total size, the exact topology, and even the ultimate finiteness or infinitude of the whole may lie permanently, structurally beyond the reach of any telescope anyone will ever build. Let's bring tonight's entire journey together and let the absence of an edge transform, one final time, from what might feel like a disappointment into something considerably closer to a genuine destination in its own right. We began tonight by asking, quite simply, where the edge of the universe actually is. And the answer, patiently assembled across everything we've walked through together, comes back the exact same way from every single direction we approached it from. There is no edge of the first kind, the kind implied by a genuine spatial boundary, because the underlying geometry itself simply forbids one. There is no edge of the second kind either, the kind implied by our own limited observation, because no such boundary has ever once been detected in over a century of increasingly precise searching, and nothing in current physics requires one to exist at all. And there is no outside for a third kind of edge to even face into, because space and time themselves are the entire arena, not an object sitting inside some larger container, waiting patiently to be discovered. The old medieval image of a pilgrim walking all the way to the very rim of the world and poking their head curiously through some outer sphere of fixed stars has no genuine modern counterpart. Not because that rim turned out to be too distant to ever reach, because reality itself, as best as an entire century of careful physics has been able to determine, simply isn't built with rims at all. Here's what quietly replaces the edge once you've let go of needing to find one. Instead of a boundary, the universe offers each of us something considerably gentler, a horizon. Not a wall, but something closer to a patient, ongoing promise. Every single year that passes, light from galaxies, sitting one additional light year farther away, finally completes its own long journey and arrives here for the very first time. Tonight, at this exact moment, photons that departed their distant source nearly 13.8 billion years ago from a shell of space that has never once, in the entire history of Earth, been visible to anyone standing on it before, are quietly striking our upper atmosphere. The visible universe, in the most literal sense available, is still arriving, patiently, a little more every single night, forever. There is a genuinely deep kind of rest available in this particular conclusion, one worth sitting with directly before we close. A universe with an actual edge would make every one of us residents of some kind of container, bounded, contained, existing inside something larger and more permanent than ourselves. An edgeless universe does something considerably kinder instead. It makes every single point, including this exact one, including you, listening to this right now, equally, precisely, mathematically, at the very center of everything there is to see. No observer, anywhere in the entire universe, is closer to some final edge of things than you are, right now, in this exact moment. There is no boundary to walk toward, no wall where the stars finally, abruptly stop, no mysterious outside, quietly pressing in from beyond. There is only the universe itself, extending all the way out, curving gently all the way around. And, in absolutely every single direction you could ever choose to look, more of it than anyone, anywhere, will ever have time to see. And that isn't a failure of tonight's journey. That is, quite simply, the actual shape of home. Let's sit with what all of this actually means, rather than rushing past it towards something more comfortable. There's a specific kind of anxiety, quiet but persistent, that tends to attach itself to the idea of infinity, or to the idea of being lost inside something too large to properly measure. It's an understandable anxiety. Most of what we navigate in ordinary life comes with edges, with landmarks, with a reassuring sense of this far and no further. Tonight's story asks you to sit, gently, with the opposite kind of fact, and to notice, carefully, that the anxiety doesn't actually have anywhere solid to attach itself once you look closely at what an edgeless universe genuinely implies. Consider what an edge would actually mean if one somehow did exist. It would mean the universe was, in some sense, a finished object, bounded, contained, existing as a kind of exhibit inside some larger, unexplained space, the way a diorama sits inside a museum case. It would raise an entirely new, considerably more unsettling question immediately. What, exactly, is on the other side of that wall? What contains the container? Tonight's careful, patient answer, that there simply is no wall, anywhere, under any of the geometries physics takes seriously, quietly dissolves that entire chain of increasingly uncomfortable follow-up questions before it can even properly begin. Not by answering it, but by showing that the question itself was built on a premise the universe simply doesn't share. There's something worth noticing, too, in how consistently tonight's story returned to the same underlying shape, no matter which specific piece of evidence or mathematics we happen to be examining. The cosmological principle showed us no center. The three permitted geometries showed us no edge, mathematically, regardless of which one turns out to be correct. The ant on the balloon showed us that finite doesn't require bounded. The library showed us that infinite doesn't require reachable. And the personal horizon showed us that the one boundary we do experience belongs entirely to us, individually, rather than to the universe as a whole. 6 entirely different lines of reasoning, arriving, independently, at the exact same gentle conclusion. That kind of convergence, in science, is usually a reasonably strong sign that you found something genuinely true, rather than a lucky coincidence of framing. There's a broader pattern worth drawing out here, one that connects tonight's story to something larger about how good science actually tends to work. Nearly every major advance in cosmology, across the entire history of the field, has followed this same basic shape. Not the discovery of some new, exotic thing waiting to be found, but the patient, careful removal of an assumption nobody had thought to question. Copernicus removed the assumption that Earth sat still at the center of everything. Hubble removed the assumption that the universe was static, unchanging, eternally fixed in size. Tonight's story removes one final assumption, arguably the oldest and most deeply embedded of them all. The quiet, almost invisible assumption that anything real must, somewhere, have an edge. Each of these removals felt, at the time, like a loss. Each one, examined more closely afterward, turned out to reveal something considerably larger and more interesting than what it replaced. And there's a specific, quiet comfort available in the honesty of Chapter 9, worth returning to directly. Physics doesn't claim to have finished this particular story. The exact topology of space, the lingering curvature anomaly, the fundamental question of finite versus infinite, all of it remains genuinely, actively open, studied by people who have made their entire careers out of patiently, carefully not knowing the full answer yet, and being completely at peace with that not knowing rather than rushing toward a premature, tidier conclusion. There is real wisdom in that particular kind of patience, worth borrowing for your own evening, whatever uncertainties you happen to be carrying into sleep tonight. Here, finally, is the thought I want to leave you with tonight. Every single point in the universe, every star, every galaxy, every quiet, unremarkable patch of empty space between them, sits at the exact geometric center of its own observable universe, in precisely the same way you do, right now, wherever you happen to be lying. This isn't a comforting metaphor stretched to fit the occasion. It's a direct, literal, mathematically necessary consequence of the exact same physics that gives every civilization, anywhere, its own personal 46.5 billion light-year horizon, centered entirely, precisely, on wherever they happen to be standing. You occupy the exact center of everything you will ever be able to see, not because the universe singled you out for that particular honor, but because centrality, in this specific and genuinely universal sense, is simply what it means to be anywhere at all, observing anything at all. There's something worth sitting with in the fact that this democratic, edgeless structure applies with exactly, precisely equal force to absolutely everyone and everything, everywhere. A civilization 30 billion light years away, if one happens to exist, is having the identical experience you're having right now, at this exact moment, surrounded by their own fog, centered on their own horizon, looking outward into a universe that shows them, in every direction, the exact same uniform, centerless texture ours shows us. There is no privileged vantage point anywhere in the entire cosmos. And rather than reading that as a diminishment, the old, familiar sting of being told, once again, that you're not special. I'd gently suggest a different reading. Every single observer is equally, fully, mathematically at the center of everything. That isn't a story about anyone's smallness. It's a story about a universe generous enough, structured deeply enough, that everyone gets to occupy the exact same best possible seat. Consider, too, what it means that a species barely 300,000 years old, standing on one small, ordinary planet, has managed to work out, with genuine mathematical rigor, the actual large-scale shape of everything that exists. Not by traveling to its edges, because there are none to travel to, but by patiently, carefully reading the faint, ancient light already arriving, every single night, from every direction at once. We didn't need to leave home to learn this. The universe, in its own quiet way, has been bringing the answer directly to our own doorstep, one photon at a time, for the entire span of human history, and for billions of years before that history ever began. There's a particular kind of humility worth noticing in exactly how this discovery unfolded, too. It wasn't achieved through a single, dramatic breakthrough, arriving all at once in a flash of insight. It came together slowly, patiently, across generations. One careful measurement of the microwave sky's temperature, one painstaking survey of millions of galaxy positions, one satellite mission after another, each contributing a slightly sharper piece to a picture no single observation could ever have completed alone. The people who did this work largely didn't live to see the full, assembled answer their own individual measurements eventually became part of. They contributed their careful piece and trusted the larger, slower, collective project to carry the work forward past the limits of their own working lives. A form of patience worth genuinely admiring and, in its own modest way, worth quietly emulating. And there's a specific kind of peace available in fully, genuinely accepting that some part of tonight's question, the exact topology, the true finite or infinite nature of the whole, may simply never be answered by anyone at any point in the future, no matter how advanced our instruments eventually become. That isn't a failure of science. It's an honest boundary on what observation itself can ever provide, arrived at not through defeat, but through genuinely rigorous, careful reasoning. There is real freedom available in that kind of acceptance. The freedom to stop needing every single question to have a final, tidy answer, and to rest, instead, inside the parts of the story that are genuinely, solidly, comfortingly settled. So let's gather up everything we've walked through together tonight, gently, before we close. We began by separating one confusing question into three distinct, separately answerable ones. The edge of what we can see, a genuine boundary in space, and the wall of some imagined container. We discovered why the universe stubbornly refuses to have a center, using the patient image of raisin bread rising evenly in an oven. We walked through the short, complete menu of shapes space is actually permitted to take, and found every single one of them edgeless by mathematical necessity rather than mere observation. We looked honestly at what our most precise instruments have actually measured, and sat, without flinching, with the genuine anomaly still being carefully argued over today. We spent real time with an ant on a balloon, learning that finite and bounded are not, in fact, the same idea at all. We wandered an infinite library, learning that infinite and reachable are equally distinct. We met the real boundary in tonight's story. Not a wall, but a horizon. Personal, patient, and gently expanding, a little further, every single year. We sat honestly with everything that remained genuinely open, from the true topology of space to the lingering curvature anomaly. And we arrived, together, at the single, quietly beautiful realization sitting at the center of this entire journey. Every observer, everywhere, occupies the exact same, best possible seat at the center of all there is to see. No dramatic, tidy ending tonight. Just an honest, careful, patient dismantling of a question that felt, at the very start of this journey, like it should have a simple answer. Replaced, gently, by something considerably larger and considerably more comforting than any simple answer could ever have been. And there is something worth carrying with you into sleep from a story built entirely around the absence of walls. Tonight, wherever you are sitting at the exact, mathematically precise center of your own observable universe. Not through any special privilege, but simply through the ordinary, universal fact of being somewhere, looking outward at all. There is no edge pressing in on you tonight, no boundary you've failed to reach, no wall anywhere marking where the universe runs out. There is only more of it in every single direction, quietly, patiently arriving a little further every single night for as long as you're here to receive it. There's a particular kind of rest available in a story built this thoroughly around the absence of endings. So much of what keeps a mind awake late at night involves the sense of something unfinished, some edge not yet reached, some boundary still waiting to be crossed before rest feels permitted. Tonight's story offers, instead, a universe that was never structured around endings in the first place, only around a horizon that arrives a little further, patiently, every year, whether you're awake to notice it or not. You don't need to reach anything tonight. You don't need to finish anything, or resolve anything, or arrive anywhere. The universe itself, on the largest scale anyone has ever measured, simply doesn't work that way. And neither, for tonight at least, do you need to. Let that be enough for tonight. Somewhere above you, right now, photons that left their source before the Earth itself had even finished forming are completing the very last, patient leg of their impossibly long journey, arriving specifically, precisely, for you, tonight, having travelled farther than any single number could ever quite capture. You don't need to chase an edge to feel the size of what surrounds you. It's already arriving, gently, on its own unhurried schedule, exactly the way it always has. Good night. Sleep well. And if tonight's journey gave you a little more to wonder about, consider liking this video or subscribing to the channel. It helps this kind of slow, patient storytelling find the people who need it. Thank you for spending these hours with me tonight. Good night and sleep well, held gently at the exact center of everything there is to see.